Hey folks, okay. Last time we said that we would find a way to go from a bunch of regular expressions for the tokens in a language to the code for our scanner or our tokenizer. So the way we're going to do it is divided up into kind of two halves. In the first half, we'll get from our regular expressions to the finite state machine that we want to use. And in the second half, we'll get from the finite state machine to the actual code for our scanner or our tokenizer. So in this video, we'll go through and look at that first half, getting from our set of regular expressions to the finite state machine that we want to use. And then in a later session, we'll cover the other half. All right, so what we're going to do is we're going to go from the regular expressions to our finite state machine, or a minimized deterministic finite automata, if I could spell right, that is. So we'll go from our regular expression to our finite state machine, and we're going to go through 3 steps. And I'm going to talk about the 3 steps now, and then we'll go through and actually have a separate video on each of them, because each of them is complex enough that we should study it on its own, but I want to show you how they fit together first. So first, it's relatively easy to go from our regular expressions to non-deterministic finite automata. Unfortunately, for producing our code, we would rather have a deterministic finite automata to work from. So we've got a couple of steps to go through. So first, we're going to use one technique to take our regular expressions and generate this non-deterministic finite automata. So the technique we're going to use is called Thompson's Construction, and we'll spend some time talking about that. Then we want to get from that non-deterministic one to a deterministic one, and we're going to use another technique for that. So the technique for that is going to be called subset construction. So after that, we've got a deterministic finite automata, but it's not necessarily going to be in minimized form. So our third step is going to be to use another technique, Hopcroft's algorithm, to go through and minimize that deterministic finite automata. And after we've done that, we'll have the finite state machine that we actually want to work from. So those are the 3 steps that we're going to go through. And again, today we're just going to walk through the process, and then in 3 separate videos we'll go through and look at those 3 steps in a fair bit of detail, those 3 algorithms in much more detail. All right, first I should take a moment. For those of you who have taken 320 already, then you know all about deterministic and non-deterministic finite automata. I'm not going to go into anywhere near as much detail on the theory. I'm not going to go into any of the proofs. I'm just going to take this stuff as more or less a given. The finite state machines that we talked about in our earlier session took a deterministic approach. They'd say, okay, we start in a state where we've read no characters, and every single character that we read as we're working our way through a token, we have a transition function that says, okay, if you're in this state and you see this character, you should go to state whatever. Sometimes that'll be staying in the same state, sometimes that'll be going to a reject state, sometimes it'll be going to some other known state. But for every combination of a state and a character, there's exactly one place to go to next. Exactly one state to go to next. So for non-deterministic machines, what we're going to say is in addition to that, they also sometimes allow you to jump from one state to another without actually reading a character in. You don't have to make that jump, but you're allowed to make that jump if you want to. And so this is where the non-determinism comes in, is that from a given starting point, there might be a whole bunch of different places you can get to with a specific input sequence, just based on whether you do or don't change to make those jumps without reading a character. So in point of fact, our non-deterministic machine, for every non-deterministic machine, if there is a non-deterministic finite automata to do what we want, then we can actually create a deterministic finite automata that will do the same thing. So if we can find an NFA, we can create a deterministic version from it. which is why we're going to go through this process. It's going to be easy to create our non-deterministic one, and then we can follow an algorithm to produce our deterministic one. So this is the idea. So the two types have equivalent power. You can prove that in 320. But again, we're going to generate our code based on the minimized deterministic version. So we'll produce our non-deterministic ones, translate them to deterministic ones, and then minimize the beasties. So just as an example of this idea of a non-deterministic finite automata, let's suppose that we've got a deterministic finite automata where we've got our start state, and we see if we see a character x, we go to state S2, and if we see anything else, we reject. Well, if we allow null transitions, maybe we add a transition in here that says, but you're also allowed, without reading any input characters, to jump to state S1 from your start state. So we'll label these null transitions and say, okay, well, there are going to be certain spots where you're allowed to jump from one state to another without reading an input. So we'll provide a specific set of null transitions that are allowed. You just can't automatically do this anywhere from state to state. But we'll specify within this finite state machine, here and here and here and here, you're allowed to jump from this state to this state if you want to, without reading an input character, without consuming an input character. So it is a little different. And again, the idea for Thompson's construction is we're going to build this incrementally. This is why it's called a construction. Thompson's construction comes up with a non-deterministic finite automata that matches a regular expression with just one single character in it. So if your regular expression is just the character A, or the character X, or the character Q, Thompson's construction gives us a non-deterministic finite automata for that character. Then what it also does is provides a set of rules that say, if you've got one regular expression followed by another, here's how you combine them into a bigger, or if you've got a finite state machine for one character and you've got a finite state machine for another character, here's how you combine them to get the concatenation of them. So for instance, if you've got a finite automata for A, and you've got a finite automata for B, it provides a rule for how you build one for AB, right? A construction rule for that. Similarly, if you've got a finite state machine for A, then it shows you how to build a finite state machine for A star. And if you've got a finite state machine for A or B, or pardon me, for A, and you've got one for B, it shows you how to build one for A or B. So it shows you how to take existing non-deterministic finite automata you already have and how to combine them together based on the regular expression that you're trying to produce. So finally, it provides a precedence order for the operations. What order should we apply concatenation or clean star or alternation in? So Thompson's construction tells us how we can take our regular expression, build a whole bunch of little non-deterministic finite automatas, so one for each individual character that's specified in the regular expression. So if your regular expression has, A, B, C, D, or E, F, G, or X star or something like that, for all those individual characters that are listed, you produce one of these non-deterministic finite automata for each individual character, and then you start applying these rules to combine those things together into bigger and bigger non-deterministic finite automata until eventually you arrive at the one for the whole regular expression. So again, this is a relatively involved process, so we'll take a look at it, we'll work through some examples and whatnot, but we'll do that in a separate session. First I want to go through and see how these pieces fit together. So once we've gone through Thompson's construction and we now have our non-deterministic finite automata that corresponds to our original set of, or original regular expression, now we want to get a deterministic version that matches that. So what we're actually going to do in this subset construction is, again, just step by step, we're going to move from the non-deterministic version to a deterministic version, and we're just going to be adding and revising states as we go. So the way it's going to work is our deterministic machine is going to have a bunch of different states, and each of them is going to correspond to a subset of the states in that original non-deterministic one. So basically, if we read a character X, for instance, we might have, in our non-deterministic machine, there might be 5 different states that we could get to. So in our deterministic finite state machine, it's going to have a state that matches those 5 states from the non-deterministic machine. So the number of states in our deterministic one can explode based on the number of possible subsets of our non-deterministic machine, but we'll work on a process to go through and just gradually build these things up. And we'll do it in a way that's reasonably efficient, well, more or less. So we'll go through this construction mechanism to gradually, step by step, build up our deterministic finite automata. So this is the notion we're going to go through for our subset construction. And again, what we'll wind up with at the end is a deterministic finite automata that matches the same language as the original, as the non-deterministic one, but it's going to have, again, it's going to be deterministic, and it's going to have a completely different set of states, if you like. So now we've gone from our regular expression to our non-deterministic automata to our deterministic automata, but there might be a whole bunch of states in this thing that are essentially equivalent. So we want to look at how to take that finite automata and produce a minimal machine from it. So that final stage is to go through and use Hopcroft's algorithm to try and minimize that deterministic finite automata. So what we're going to try and do is identify sets of states in the deterministic machine that are equivalent. And the idea is 2 states are equivalent if they produce equivalent behavior across all possible inputs. So we'll talk about what it means to produce equivalent or identical behavior across all inputs as we get into Hopcroft's algorithm. But essentially, it's going to take our original set of all the states in our deterministic machine, and it's going to keep partitioning them based on ways where it identifies one of those states is different than others. So cases where it says, oh, on this input, these states go this way, and this other state or these other states go this other way. So we're just going to keep partitioning our sets into smaller and smaller subsets until we can't distinguish them any further. And then we're going to say, that collection of subsets now is the set of states in our minimal machine. So we'll start with this process, right? The first step is going to be essentially just to say, well, accept states are different than non-accept states, so we can come up with a quick partition there. And then we'll repeatedly go through this process of saying, okay, let's pick one input character and see if all of the characters in one of our sets takes us to the same other collection or the same other set of states, is essentially the way it's going to go. And we're going to keep doing that as long as we can keep finding ways to partition the existing sets that we've got. So again, we'll spend a separate session going through Hopcroft's algorithm to see how it works and to look at the efficiency issues around it. And by the time we get to the end of that one, now we've got a minimal finite state machine, and all we have to do is turn that into actual code for our tokenizer. But again, that'll be the second half of our process that we'll cover after we've gone through Thompson's and subset construction and Hopcroft's. All right. If you want to go through and start taking a look at what Lex might do, right? Lex is going through and it's got some kind of automated process for going from our regular expressions to a tokenizer, so it's got to be doing something. Now, if you're interested, you can start browsing through, when you do your make on your Lex and Yak files, you'll see that one of the things that it produces is the lex.yy.ca, and this is essentially the tokenizing code that it's producing, the scanning code that it's producing. And if you start digging in, you'll see a finite state machine buried in there with a while loop that's cycling through the inputs and a set of states. You'll see code in there to go through and read the source code, and as it's going through identifying tokens, you'll see it setting up YYL values and YY text values. And you'll see spots within this kind of while forever, or do forever, while forever loop. You'll see spots that match your the code that you produced in your .lex file to identify the different token types. So you can start browsing through and see if you can spot what Lex is actually doing. But we'll leave that for another day. That's just sort of food for thought. So again, next time what we'll do is we'll go through Thompson's algorithm. Then after that one, we'll spend some time going through subset construction. Then after that one, we'll spend some time going through Hopcroft's algorithm. And then once we're done with all of those, then we'll start looking at how we can take our finite state machine and eventually produce some source code from it. All right, that is a good place to stop for now.